Find the below for the function f of x equals x squared minus 2x minus 3 over x squared plus 5x plus 4. So this is a rational function. So first it says as to find the domain for the function. In order to find domain, if we can factor, we need to factor the numerator and denominator. So numerator factors 2. We write in parentheses first. Is x minus 3, x plus 1. Denominator factors 2, x plus 4, x plus 1. So for finding domain, we do not cancel anything out. We just look at the denominator right here, and what values can we not have? Right. So let me write the answers here for A. For A right here, domain is negative infinity to negative 4, negative 4 to negative 1, negative 1 to positive infinity, because we have to exclude negative 4 and negative 1. Now, when we're finding vertical asymptote, this is when, for purpose of finding vertical asymptote, we can cancel out common term from top and bottom, if there are common terms. So for vertical asymptote, we have this as a function. Again, this is just for vertical asymptote. We can cancel out that, you know what, x plus 1 cancels out. So we have x minus 3 over x plus 4. And whatever makes this simplified term undefined, in this case negative 4, is a vertical asymptote. So you have only one vertical asymptote in this case, x equals negative 4. Again, this simplifying is just applicable for finding vertical asymptote. That's why we're finding domain first. And let's look at horizontal asymptote. Horizontal asymptote, we have three options, three different types. Here, the degree of the top and degree of bottom is same. Right? When they're same, what we do is we divide this coefficient of the highest degree of top and bottom, which is in this case 1. So horizontal asymptote is y equals 1. And let's find x and y intercepts. For x intercepts, well, let me actually show work in the other parts. For x-intercept, what we do is we solve this function equals 0. So when is x minus 3, x plus 1 over x plus 4, x plus 1 equals 0? Well, fraction can be only 0 when numerator is 0, right? So essentially, for rational function, for x-intercepts, we're looking at when is the numerator 0. Is numerator 0 when x is 3 and x is negative 1, right? But negative 1 is not in the domain, as we found it here. So this is not an x-intercept because it's not part of the domain. Therefore, x-intercept is 3, 0. Oops. 3, 0. For y-intercept, we just plug 0 for x. Right, we do f of 0. And I plug 0, and then I get 0 minus 3, 0 plus 1, over 0 plus 4, over 0 plus 1. Then I get negative 3 on the numerator, positive 4 on the denominator. So y-intercept is 0, negative 3 over 4. So now that we have all this information, let's try to sketch this. So what I suggest is first mark the domain. Like we know that at negative 4 and negative 1, we should not have any values. Right, so keep that in mind. So either you should have an open circle indicating a hole or vertical asymptote in these two numbers. But we know that only a negative for a vertical asymptote. Oops. That means that negative 1 along the graph on the y value, we should have open circle somewhere. Okay. So keep that in mind. And let's plot horizontal asymptote, y equals 1. Let's say 1's here. Something like this. Okay. And let's plot x and y-intercept 3, 0, 1, 2, 3 right here. 0, negative 3 over 4 is somewhere here. Okay. So when you graph this, when you graph rational function, try to graph one section at a time. And how do we know the section? The sections are divided by vertical asymptote. So here you can think as we have one section here left side of the vertical asymptote and another section right side of vertical asymptote. So draw one section at a time. Okay. So let's draw this part first. So here we don't have any points, right? So we can try some points. We can plug some points. Maybe we can plug -5 and -6 to see what value we get in the function. So if I plug -5 and -6, what do I get? And they will kind of tell us the trend of the graph. Okay, so I can plug it here. Get -5 minus 3, -5 plus 1 over -5 plus 4, -5 plus 1. That gives me -8 times -4. -8 times -4 is positive 32 in the numerator. This is -1. -1 times -4 gives me positive 4, which is 8. Okay, and let's do -6. This is -9 times -9 times -5, which is positive 45. -2 times -5 is positive 10, which is 4.5. So that means that when x is -6, it's 4.5. Let's say maybe somewhere here. 4.5 is somewhere here. 4.5. And 8 is way above right here, let's say. Okay, something like this. So this tells us that, you know what, the graph has trend of something like this. Okay, actually, let me make it better scale so we can draw real nicely. So I'm actually have a different scale for y-intercept. So let's say here's 1, 2, 3, 4, 5, 6, 7, 8. So here's the horizontal asymptote. So at -6, 4.5 somewhere here, y is 8. So here at -5. So the graph has this shape on this side of the graph. Again, it's approaching, so that's why you need to arrow. So eventually you will get very close to vertical asymptote on the left side. Okay. Let me draw the curve a little better. More curve like this. Okay. Oops. That's the left side. On the right side of the vertical asymptote, we already have 2 points. So we know that, you know what, it has to approach horizontal asymptote like this. And it goes this way. Vertical asymptote going -infinity here. So the final answer is both of these graphs, this part and this part. And actually, I forgot to do one thing, right? You know what that is? At -1, we should have open circle here, actually. At -1 is not defined. So when we sketch this, make sure to draw open circle here and connect this like this. So we should have open circle here. So the final answer is this graph right here and this graph. Open circle here and like this. This is the final graph of this function. Sketch of this graph. Find the below for the function x plus 4 times x plus 1 times x minus 3 over x plus 1. So let's find the domain first. When we find domain, again, we don't simplify anything. Just look at the function as given. What can we not have in the denominator? negative 1, right? Then we have 0. So domain is negative infinity to negative 1 and negative 1 to positive infinity. Now for vertical asymptote, we have to simplify if we can. If you cannot simplify, then we just don't simplify and find whatever makes undefined. So in this case, we can simplify. So this simplifies to x plus 4 over x minus 3. Nothing in the denominator, right? So here, nothing makes this undefined, right? This is always defined, right? Let me write that a little better. X plus 4 times x minus 3 is always defined. There's no x value I can plug it in to make it undefined, right? So there's no vertical asymptote for this rational function. Okay. So let's look at horizontal asymptote. For horizontal asymptote, we have 3 types. In this case, we have to look at the degree of top and degree of bottom. So on the top, the degree of top is, if I were to multiply this out, I get x cubed as the highest degree. And there's no coefficients, only x, right? X, and x, so I have x cubed on the top. And denominator I have x, right? For the highest degree. When the top degree is higher than the bottom degree, there's no horizontal asymptote. Right? So this is no horizontal asymptote. Okay. And let's find x and y-intercept. For x-intercept, solve entire equation equals 0. So when is function 0? When f of x plus 4, x plus 1, x minus 3, x plus 1 equals 0. This is 0 when numerator is 0, right? When fraction. So we have negative 4, negative 1, 3. But negative 1 is not in the domain, right? Like right here. So only x-intercepts are negative 4, comma 0, and positive 3, comma 0. Now don't confuse here. This is an interval for x. This is x-intercept. When x is negative 4, y 0. When x is 3, y 0. Right, so don't confuse in those two notation. This is a coordinate order pair, where this is both referring to x values of domain. Okay. Y-intercept, we just plug 0, f of 0, and see what we get. We get 4 times 1 times negative 3 on the numerator, and 1 in the denominator, which is negative 12. So 0, comma negative 12. So let's plot these. Let's graph this function. Again, remember, when we're sketching this, it's important to do domain first. So at negative 1, we should either have vertical asymptote or an open circle or hole representing that negative 1 is not in the domain. Since there's no vertical asymptote, that means we should have a hole at negative 1 for the y value of the graph. Okay. So let's sketch this first and we can figure out. So this function has 0, comma negative 12. So let's say 0, comma negative 12 is here. And 3, comma 0, negative 4. Okay, so let's go through these 3 points, right? So function will have this shape because connected 3 points, right? Something like this. But now here is open circle, right? So you have to have an open circle and negative 1. Let me actually draw more precisely. Open circle here. So it's almost a parabola, but it is not because it's a domain negative 1 is not in the domain. So final answer is this this, and open circle here. Make sure you draw the other color or thinner. So this open circle, and this is the final graph. Okay. Find the below for the function 3x squared minus 2x plus 1 over x minus 1. So again, when we find the domain, first find the domain. Again, we don't actually have to worry about factoring, right? Because we only need to look at the denominator. What makes denominator does not exist, right? In this case, x equals 1. So domain is negative infinity to 1, union 1 to infinity. So then for finding vertical asymptote, we do have to factor. So let me actually factor the numerator. We get 3x and x, and it should be minus 1 plus 1. Okay, minus x. Oops, let me see. Let me double check. Actually, if we do plus 1 and minus 1, actually, I don't think it's factorable. Let me try again, though. Plus 1 and minus 1. I get x negative 3x. Yeah, it doesn't work because then we have to positive 1 here, right? But positive 1 times negative 1 give us negative 1. So this is actually not factorable, which is fine, okay? That means since it's not factorable, this is as simplified as we can write it. So whatever makes the denominator 0 will also give us the vertical asymptote. So in this case, vertical asymptote is x equals 1, which is also not in the domain, right? So that means that for this graph, we do not have an open circle or a hole. Okay. Let's look at horizontal asymptote. For horizontal asymptote, the one with a degree higher than bottom, we don't have a horizontal asymptote, right? So no horizontal asymptote. Okay. So we're going to graph this. Well, let's find the x and y-intercept first. And I'll tell you something else. Well, x-intercept will actually solve this equal to 0, right? We've said function equal to 0, but we only care about numerator 0, right? Because denominator cannot 0. Okay. So this one is not factorable, so we have to use quadratic formula, which is minus b plus minus b squared minus 4ac over 2a. So here we'll see that actually when I do this part, b squared, which is negative 2 squared, positive 4, minus 4 times 3 times c, which is 1. This is negative 12. Well, this is negative 12, right? 4 minus 12. So this portion is actually negative 8. So this part actually gives us negative 8. But we cannot have a negative number on the square root, right? So there's no rational number or real number that will make this true. That means there's no x-intercepts. Okay, so no x-intercepts. And that's okay. So, it's okay for graphs to not have x-intercept. It just doesn't intersect with x-axis. For y-intercept, plug 0 in, f of 0. We'll get 1 in the numerator, negative 1 denominator, so negative 1. So 0, comma, negative 1. So we have 0, comma, negative 1 somewhere here. Now this one, if you look at this graph, when the degree of top is exactly 1 greater, when degree of top is exactly 1 greater than the bottom, this 1 is implied, right? Then this actually has a slant asymptote, or also known as oblique asymptote. So we actually need to find oblique asymptote to graph this. Again, the way we know that this has oblique asymptote is by looking at the degree. It's on 2 right here. This is only exactly 1 by greater by only 1, right? 2 is only bigger than 1 by 1 amount, right? So that's how we know. That's how we recognize there's a slant asymptote. Even if it doesn't tell us, that's how we know. So then in order to find slant asymptote, we have to divide. We do 3x squared minus 2x plus 1 divided by x minus 1. Do long division. Okay. And whatever the quotient is, will be the slant asymptote. So let's do that. First, I need to have multiply by 3x to get 3x squared. Negative 1 times 3x gives me negative 3x. Subtract gives me x. Right? Negative 2 minus negative 3x is positive 3x. Positive 3x minus 2x gives me x. And then I need to multiply by 1 to x times x. 1 times 1. This plus 1 comes down here too. Well, actually, comes down here, plus 1. Subtract. I get 0 for x. 1 minus negative 1 is 2. So remainder is 2. But remainder, we're not actually concerned with remainder for finding slant asymptote. Right? Once we have the remainder, remainder, just look at this. This is slant asymptote. So y equals 3x plus 1 is the slant or oblique asymptote for this function. So if 1's here, slope is 3, right? That means rise 3, 1, 2, 3, and go over by 1. So 2 points. I should draw that a little better. It's 1, 2, 3, 4. So we start at y equals 1, y-intercept 1. 1, 2, 3. And go over by 1. So connect these two dots. Well, this is slant asymptote. So it's actually not part of the graph, but we need to have this drawn so that we will know the shape of the graph. Okay. So this is a slant asymptote. Let's sketch also the vertical asymptote, which is x equals 1. X equals 1, let's say somewhere here. Yeah, right here. And this right here. Okay. Like this. Okay. So we know, at least for the, so here we actually, again, have a one section. Left side of the vertical asymptote and another section, right side of the vertical asymptote. Well, left side, we have this point, right? So we know that this graph will, so we know here that this left side of the vertical asymptote has this shape. On the right side, we have to pick a point. Let's pick number 2, for example, and plug 2 here. See what I get. So let me do on the side right here. F of 2 is 3, 2 squared minus 2 times 2 plus 1 over 2 minus 1, which is 12 minus 4 plus 1 over 1, which is 9. Right? 9 in the top, 1, 9 over 1 is 9. So it's all the way up somewhere here. Again, we're kind of sketching the generic shape. So we know that here, it should have shape of something like this. So for this function, it has shape of this one and this. Both these are part of this one function graph. Okay. So again, for this one, we should recognize that there's a slant asymptote because 2 is exactly 1 bigger than the numerator's degree. For the below function, find the below. So let's find the domain first. So in order to find domain, it's helpful to, if it's not factor them. Right. So here, this is factorable to 2 plus x, 1 minus x. So in this case, we cannot have negative 2 and 1. Right? So domain is negative infinity to negative 2. Union negative 2 to 1. Union This is not U, this is union sign. Union, 1, 2, positive infinity. So that means that at -2 and -1, I'm sorry, -2 and +1, we should either have vertical asymptotes or open circle, hole, representing that domain, for x equals that value, y value does not exist. Because the x value itself is not defined there. Okay. So when we find the vertical asymptote, we need to simplify this if we can. But this is not factorable anymore, right? The numerator is not factorable. So this, we cannot simplify this anymore. Then whatever makes this, the denominator makes it undefined, we get vertical asymptote. So in this case, x equals -2 and x equals 1 is, these two are vertical asymptotes. Again, if we can further simplify this more by numerator and denominator, then we have to exclude those values. But in this case, nothing can be cancelled out. Horizontal asymptotes. These two are same degrees, right? These are the highest degrees, 2x squared and -x squared. They're same degree. When they're same degree, we divide by the coefficient. So we have 2 over -1, which is -2. Right? So y equals -2 is the horizontal asymptote. When the degree is same, we divide by the coefficient of the highest degree of the numerator by the coefficient of the degree of the denominator. Let's find x and y intercepts. For x-intercepts, set function equal to 0. So 5 plus 2x squared equals 0. Right? Because in order for a fraction to be 0, only numerator has to be 0. Because denominator cannot be 0 anyway. And 0 divided by a number gives us 0. So solve for x here, -5. X squared equals -5 over 2. But x squared cannot be a negative number in real numbers, right? So there's no x-intercepts. No x-intercepts. And that's okay. That just means the graph does not intersect with x-intercepts. X-axis, sorry. For y-intercept, plug 0 in. We'll get 5 over 2. Right? If I plug 0 here, 0 here, 0 here, right? I get 5 over 2. So all I have for intercept is 0, 5 over 2. So let's plot this. 0, 5 over 2. There's 1, 2, 3, 4, 5. So 5 over 2 is about 2, is exactly 2.5, right? So somewhere here. The graph will intersect here. And we have a vertical asymptote at x equals 1. X equals -2. And y equals -2 for the horizontal asymptote, like here. Okay. So now when we graph this, again, we're graphing one section at a time. Here's the one section. Here's the, oops, sorry. Here's the second section and third section. So draw one section at a time. So what we have to do is we have to plug some points. So let's plug maybe -3 and -4 to the function right here. So plug f of -3, f of -4 to see what y value we get. So we can kind of know where these are, here or is it here. Okay. When I plug -3, I get 5 plus 2 times -3 squared over, I can plug it here, easier calculation. 2 minus 3, 1 minus -3. I get 5 plus, that's 9, 18. -1 times 4 gives me 23 over -4. So -23 over 4, which is close to -6, but slightly bigger, right, since it's negative. So if there's -6 is here, slightly bigger than negative 6, so it's a little above. If negative 6 is a little above negative 6, somewhere here. Okay. So let's see when we get negative 4. We put negative 4. 5 plus 2, negative 4 square. 2 minus 4, 1 minus negative 4. We get 16 times 2 is 32. So 5 plus 32 over negative 2 times 5, which is 37 over negative 10, which is negative 3.7. So it's bigger than this value. So negative 3.7 is somewhere. Here's negative 3, negative 4 between these two, right? So somewhere here. And these two are enough for us to give us a trend. A vertical asymptote, we know it has to go like close to vertical asymptote. So go negative infinity here, and it also approaches horizontal asymptote like this. So we just draw the one section. Let's look at the midsection. So again, the midsection right here, it could be, we don't know, it could be like this, or this. There are several options. And also note that it is possible to cross horizontal asymptote. That's okay. It's just the graph cannot pass vertical asymptote because the functions are not defined. But it's okay to cross horizontal asymptote. Right? Make sure to remember that. So here we know LSC passes 1 point. Right? So let's plug two numbers. Let's plug this one right here, negative 1. What does f of negative 1 give us? 5 plus 2, because negative 1 squared is 1, right? 2 minus 1, negative 1 minus 1, which is 2. Right? Minus negative is plus. This is 1. So we have 7 over 2. So around 3.5. Or exactly 3.5, sorry. So 3.5 is somewhere here. Okay. So then let's plug a number right side of this y-intercept, because right now function could go like this or it could go like this. We don't know until we know one more point. So let's plug half. So let me plug half right here. F of half give us 5 plus 2 times 1 over 2 square over 2 plus half, 1 minus half, which give us 5 plus, this is 1 over 4. So 2 times, this right here is 1 over 4, right? 2 times 1 over 4 gives me actually half over 2 plus 1 over 2 gives us, this is 4 over 2, right? I can have a common denominator, so I have 5 over 2 plus half. So 5 in common denominator is 10 over 2. So I have 11 over 2 over 6 over 2, which is 11 over 2 times 2 over 6, which is 11 over 6. 11 over 6 is a little, oh, sorry, I made a mistake here. This should be multiply here, right? So let me erase that. So we have still 11 over 2 on the numerator. This is 5 over 2 times 1 over 2 is 5 over 4, which is 11 over 2 times 4 over 5, which is 44 over 10, which is 4.4, right? Sorry, running out of room, 4.4. So when x is half is 4.4. 1, 2, 3, 4, somewhere here. So if this 3 points, which means function has to have some kind of this shape right here, parabola. Okay, because we know the trend of vertical asymptote is that it either has to approach infinity or negative infinity. So in this case, both goes to positive infinity. So this is the second part of the graph. Now we have to draw the other part right here. So here we pick 2 points. Let's pick 2 and 3. Okay. Kind of running out of room, so I'm going to actually do on the next page. So let me do it here. f of 2 and f of 3. F of 2 is 5 plus 2 square over, let me see, 2 plus 2 times 1 minus 2, which gives me 13 on the numerator. 4 times negative 1 gives me 13 over negative 4, which is negative 13 over 4, which is close to negative 3, but smaller, right? This is negative. So negative 3 is here, but it'll less than negative 3 because 13. If it was 12, it's exactly negative 3, right? So we can plot somewhere here, a little less than negative 3, get negative 2. Oh, sorry, positive 2, when x is positive 2. So let's see when x is positive 3. Oops, 2 plus 3. 1 minus 3. We get 9, 18. 5 plus 18. Over 5 times negative 2 gives me, what is it, 23 over negative 10, which is negative 2.3. Negative 2.3, here's negative 2. Negative 2.3 is close to negative 2 from the bottom. So now that we have these two dots, we know the graph should be some of this shape right here, like this. Okay, so let me go back to this graph. So final answer is all these three parts. This one right here, this one, and this one. All these three parts are graph of this one function, one rational function. There's two vertical asymptotes and one horizontal asymptote.